So, Samuel, machines learning from experience? It sounds fascinating, but how exactly does this work?
Well, imagine you're teaching a dog a trick. You show it the desired action, and reward it when it gets it right. That's kind of how a learning algorithm works.
Okay, but what's the technical equivalent of the treat?
The algorithm is fed input data with corresponding desired outputs.
So like showing the dog a sit command and rewarding it when it sits?
Exactly. The algorithm learns the relationship between the input and the output. Then, when it sees similar new data, it can predict the output.
Makes sense. But what if the input and output are very different? Like an image and a description of that image?
That's where deep learning comes in. It's really good at finding complex patterns in data, even when it's not immediately obvious. It's like teaching the dog to identify different objects, even if the description is complex.
So, it's not just about recognizing the same image?
Exactly. It can learn the connections between things that seem very different, like the visual features of an image and the words that describe it. It finds hidden relationships.
That's cool. But what if the new data is very different from the training data? Will it still work?
Deep learning can handle that. It's designed to adapt and learn even if the new data is from a different domain. It extracts general features.
So, the algorithm figures out the features even if the input and output are totally dissimilar?
Yes. Like recognizing a dog in a picture taken under different lighting conditions. The algorithm has learned those features and can apply them even in completely new situations.
Fascinating. So, how is this different from, say, traditional algorithms?
Traditional algorithms often need very specific data structures, very clear boundaries. Deep learning can handle more complex data, like images and text, because it learns hidden patterns.
So, deep learning is like a superpowered version?
You could say that. It can find patterns we humans may not even recognize. But it also needs tons of data to be effective. That's a crucial detail.
A lot of data?
Yes. A critical point. The more data, the better it performs, but it needs quality data as well.
So, Samuel, Kepler's meticulous work, 6 years of staring at data. It's fascinating. How does this relate to modern deep learning?
It's a fundamental principle, Alfred. Kepler, had a set of data points. He was trying to find a way to describe them.
Yeah, but without computers. That's the real head-scratcher.
Exactly. He had to try different shapes, find the best fit. That's what we do in deep learning. We're searching for the best mathematical function to represent data.
So, the simplest possible model? Is that like Occam's razor?
Precisely. Kepler chose the ellipse. In modern
In this iterative process, adjusting parameters till the model fits.
That's the heart of training algorithms. We adjust the parameters of a function, be it weights in a neural network, until the predicted output matches the desired output. It's trial and error, refined by feedback loops.
So, he essentially used a validation set?
You got it. He had some data for finding the shape and another set to check if his model was any good. Absolutely essential.
A neural network could have fitted those trajectories without an ellipse. Is that a point of comparison?
Absolutely. Neural network.
But if a neural network is so flexible, why not just use one for everything?
It's not always the best approach. A model tailored to a problem often has fewer parameters and learns faster. Neural networks are great for complex tasks, but they require a massive amount of data. Kepler needed much less.
So, the underlying model in data learning isn't necessarily engineered for one specific task?
Correct. We look for models that can adapt to a range of similar tasks with the right data.
So, we're not limited to using deep neural networks in deep learning?
Not at all. The idea is to have generic models capable of being adjusted to specific tasks. PyTorch allows us to easily create and adjust these models with the calculations needed.
So, the book is aiming to make this process easier and transparent?
Precisely. We're starting with simpler models to understand the fundamental mechanics, and moving towards the more complicated ones in the next chapters.
So, Samuel, learning is just parameter estimation? That's a pretty radical idea. Explain that to me.
Yeah, it's a powerful one. Think of it like fitting a curve to data. You've got these points, you need a curve that explains them, and the parameters of that curve. That's what you need to estimate.
Okay, so we're looking for these, parameters? What kind of parameters are we talking about here?
Exactly. In a model, they might be the slope and intercept of a line, or the coefficients of a more complex function. In a neural network, these are the weights.
Weights? Like the weights of the network?
Exactly. And those weights define how the network processes information. So, finding the right weights, that's what learning is all about.
And how do we find them?
We use data, a model, and an algorithm. We feed the model our data and initial guesses for the weights. Then we calculate how good our predictions are by comparing the model's outputs with our expected outputs, the ground truth.
Ground truth. Sounds important. So, we measure the error.
Yep, the error between our predictions and the truth. Then we use calculus to figure out how changing the weights affects the error. That's the derivative, or the gradient.
The gradient. Okay, so we're trying to minimize that error by adjusting the weights.
Exactly. We update the weights in a direction that decreases the error. We keep doing this until the error is acceptably low, measured on data the model hasn't seen before, called unseen data. This whole process is called gradient descent.
So, you're basically searching for the optimal parameters. Makes sense.
It's a bit like finding the lowest point on a hill, you know? This is why this model is so important. You start somewhere and just keep going down the hill.
You compare our predictions to the ground truth, then adjust. What if we get stuck in a local minimum?
That's a great question. It's a common pitfall. A local minimum is like a small valley. We might find the lowest spot in our immediate area, but there could be a much lower spot somewhere else. So that's why we often use different optimization techniques or different starting points to avoid those problems.
Interesting. And this whole process, is it just for neural networks?
No, not just for neural networks. We use it for all sorts of models, even simple linear regressions. The core idea of finding the optimal parameters is universal across machine learning.
So, we've got this fancy thermometer, but it doesn't show units. A bit of a problem, right?
Yeah, it's a bit frustrating. But it's solvable. We can use machine learning to figure out the temperature.
Machine learning? How does that work? Explain it like I'm 5.
Imagine we have a bunch of temperature readings, and we know what the actual temperature is for each one. That's our data set.
Okay, so like a chart?
Exactly. We use a computer program, a model, to find a relationship between the readings and the real temperature. We adjust the model settings, a bit like tuning a musical instrument, to make the predicted temperatures close to the actual ones.
And PyTorch? What's that?
PyTorch is a toolbox to build and use these models, to make this kind of data analysis easier.
So, it's like we teach the computer to predict?
Exactly. We're essentially training the computer to recognize patterns in the data, to learn the relationship between the thermometer reading and the temperature, making it so we don't need the units.
Sounds pretty cool. What if our data is a bit wonky? Like, not all measurements are perfect?
That's a great question. The cool thing about machine learning is that it can still work with messy data.
So, we're basically doing what Kepler did, but with a superpowered computer tool?
Exactly. We're using modern tools to tackle a problem that's similar in spirit to Kepler's work, but we are able to work much faster and with more complex data. It's a great example of how advancements in technology can make scientific inquiry more powerful.
That's amazing. So, in the end, we get an accurate reading without needing the units?
Absolutely. We can then use the trained model to predict temperature just from the thermometer reading.
Makes sense. Very cool. Thanks, Samuel. So, Samuel, we've got this temperature data. What's the deal with these T_C and T_U values?
Right. T_C represents temperatures in Celsius, standard stuff. T_U, though, those are our unknown units, potentially a different temperature scale, or something else entirely.
Interesting. Why unknown units?
Well, we're collecting data from a new thermometer. Maybe it's calibrated differently. We need to figure out how to convert it to Celsius.
So, we've got both Celsius measurements and these mysterious ones. How do we connect them?
Precisely. We'll use a model to figure that out. The data's already in these tensors. That's just a fancy way of saying, organized datasets for our calculations.
Tensors? What are those exactly?
Basically, multidimensional arrays.
Think of them as specialized containers for numbers. Makes calculations way easier, especially with big datasets.
Okay, so we have Celsius and these unknown values. What are we trying to estimate?
We're trying to find the relationship between the two. We want to estimate a formula to convert unknown units to Celsius.
Got it. So, we're looking for a conversion formula. But why the need for noise in the measurements?
You know, measuring devices aren't perfect. There's always some error, some little inconsistencies. Plus, the readings are based on some approximation. This noise is part of the process, and we need to account for it.
So, we're gathering Celsius and these weird measurements. And we're looking for a formula to convert the mystery data into Celsius. Why the 2 weeks to gather this data?
It takes time to build up a good dataset. You need a substantial enough amount of data points for any meaningful conversion, so we're collecting over a couple of weeks. We need enough samples to accurately model the relationship between the two.
Makes sense. We're trying to figure out how to use this data for conversion, which is important. And are there any common mistakes or pitfalls we should watch out for?
Yeah, a common pitfall is ignoring the noise. You could end up with a model that fits the noise rather than the actual relationship. Also, the dataset has to be representative. Not having a good range of values could make it hard to get a good model.
So, basically, we have to be careful about the noise and have a good data range to get a precise conversion formula, right? So, Samuel, this figure, it shows some data. Seems noisy, right?
Yeah, definitely. Scattered points. But, importantly, we think there's a pattern.
A pattern? Like what? What are we looking at?
Well, the caption suggests a linear model might fit. It's hinting at a relationship where temperature changes in a predictable way with measurements.
Linear model? Like a straight line? That's interesting. How would we know if that's correct?
Right. It's a pretty common starting point. If the data does follow a straight line, it would make finding a pattern much easier. Finding the straight line through the scatter plot helps to determine that relationship.
Okay, so this graph, this is kind of like a starting point?
Exactly. It's a visual exploration. A good first look. We're looking for structure.
But what if it's not a straight line? What if it's more complicated?
Then we'd need a different model. This is part of the modeling process. The simplest explanation is often the best. But a more intricate model might exist.
Fascinating. So, this visual check is just step one, right?
Absolutely. It's crucial. It helps us decide what approaches to try. We have to visualize the data to understand what we're working with.
So, Samuel, we're talking about this linear model for converting measurements. It seems pretty straightforward.
Yeah, it's simple but powerful. We're essentially looking for a relationship between two sets of temperature readings.
And you're saying it's likely that they're related linearly?
Probably. Let's start with the simplest case. If they're linearly related, we can express the Celsius temperature as a weighted value of the other temperature plus a constant offset.
So, like finding the slope and y-intercept of a line?
Exactly. We need to find those values, W and B. And that's where the data comes in.
How do we find the best W and B?
We need to use the data to figure out the best values. We want the predicted Celsius temperatures to be as close as possible to the measured Celsius temperatures.
So, you're looking for a perfect match?
Not necessarily a perfect match. We're looking for a model that minimizes the errors between the predicted values and the real values.
And that's where the loss function comes in.
Exactly. The loss function measures the errors. A high error means a high loss. We want the loss to be as low as possible. Ideally, the best W and B values minimize the loss function.
So, essentially, we're trying to find the W and B that result in the smallest difference between our predictions and the actual temperatures?
That's right. And that process is called optimization. We're finding the minimum of the loss function. This concept applies very broadly, not just to linear models.
Interesting. So, with more complicated models, it becomes a bit more challenging to find the ideal parameters?
Absolutely. Imagine something like a neural network. Finding the ideal parameters becomes significantly more complex, but the same core principle applies. using the data to minimize the error.
Makes sense. Thanks, Samuel. Okay, Samuel, so we're aiming for minimal loss, right?
Absolutely. Loss functions are crucial. They tell us how well our model is doing.
And these loss functions, they quantify the difference, right?
Exactly. They quantify the difference between what the model predicts and the actual values.
So, how do we choose the right loss function?
Well, we want a function that helps us converge toward the right answer.
So, you're saying we want something that gives us a positive value when predictions are off?
Precisely. We need a function that makes the error positive when the prediction is too high or too low.
Like absolute value or square difference?
Yeah, both work. Absolute difference, just the raw distance, is simple.
So, is the square difference better?
Often, yes. Square difference is better because mathematically, it helps us zero in on the perfect point more effectively.
You mean its derivative behaves more nicely?
Precisely. The derivative of the squared difference is defined at the exact point we want to converge, which is where prediction equals true value.
Interesting. So it's smoother around the minimum?
Yes.
That's what I was getting at. Smoothness, right?
Exactly. It's more stable for our algorithms to work with.
And the squared one punishes large errors more?
Yes, exactly. Often, a few minor errors are better than one or two major ones, and the squared difference emphasizes that.
So, we're aiming for that smooth, stable squared difference.
That's the plan for now.
Great. Makes sense. Thanks, Samuel. So, we got our model and loss function. Now, how do we actually train this thing? You mentioned PyTorch, right?
Yeah, PyTorch makes this super straightforward. We've defined our model, a simple linear equation.
A simple linear equation? Tell me more.
Exactly. We're just multiplying the input by a weight and adding a bias. It's like a fundamental building block.
So, we have this tensor, these values. How does PyTorch actually fit that?
We initialize the weight and bias as tensors with specific values, and then our model function applies the linear equation to our data.
Okay, so we're talking about gradient descent?
Precisely. We use the loss function to figure out how far off our predictions are from the actual values.
And how does that help determine the best weights and biases?
The loss function gives us a measure of error. We want to minimize that error, and PyTorch's powerful gradient descent algorithms are designed to adjust the weights and bias iteratively to find the values that minimize this loss.
So, the whole magic is in the loss function?
The loss function quantifies the error. By iteratively tweaking the weights and bias, we gradually reduce the loss to its minimum. It's all about optimization.
You mentioned broadcasting. What exactly is that?
Broadcasting is how PyTorch handles operations on tensors of different sizes. It expands smaller tensors to match larger ones to perform element-wise operations efficiently.
So, it's like a rule for PyTorch to handle the matching?
Sort of. It's a smart way of making operations work without needing to explicitly adjust all the shapes, so it's a significant efficiency booster. Think of it like fitting different-sized pieces of a jigsaw puzzle together. PyTorch handles the alignment automatically.
So, for example, a weight or a bias value that is a single number can be used with a whole vector. Neat.
Exactly. That's the beauty of broadcasting. It simplifies a lot of tensor operations.
So, this broadcasting in PyTorch is essential for practical use.
Absolutely. Crucial. You'd see it in a multitude of machine learning models, especially for linear operations.
So, Samuel, we're talking about gradient descent. It sounds simple, but how does this fiddling with knobs actually work in practice?
Well, imagine you're trying to find the lowest point in a valley. You don't know the exact path, so you just start somewhere.
Right. Like blindfolded?
Exactly. You feel the slope, see if it's downhill. Then you take a step downhill. You repeat this, always going downhill, until you hit bottom.
Okay, but how do you know which way is downhill?
That's where the gradient comes in. The gradient is like a compass, pointing the direction of steepest descent.
So, the gradient tells you the direction of the steepest downhill slope?
Yes, the gradient tells us which way the loss function is changing the fastest. We adjust our knob's parameters in that direction.
And you said this slows down as you get closer to the minimum?
Exactly. The slope gets gentler as you near the bottom of the valley.
So, you adjust less and less with each step? Makes sense.
And critically, if you go too far, you might climb up a hill. That's why we're not just blindly moving down, but also adjusting our step size.
So, how do you know if you've hit a minimum?
You look for a point where the gradient is close to zero. That means you've found a local minimum.
A local minimum?
That's right. This algorithm finds the nearest minimum, but might not find the absolute global minimum. That's just something to keep in mind. Sometimes another algorithm is needed, but gradient descent gets us really close, especially in deep learning with many knobs.
Interesting. So, this valley metaphor is helpful. Is there a real-world example of this kind of optimization?
Definitely. Imagine you're trying to train a machine learning model to recognize images. The knobs are the model's parameters. The loss function measures how well the model is doing. You want to adjust the knobs to minimize the errors, making the model better at recognizing images. The gradient points the direction of greatest improvement in image recognition accuracy.
Okay, Samuel, so we're talking about gradient descent now. It's like fine-tuning a knob, right?
Exactly. We're trying to adjust parameters to minimize loss.
And you measure the change in loss by adding a little to the value?
Yeah, a tiny bit. See how it affects the loss. That tells us the slope.
So, you're calculating the rate of change?
Precisely. If the loss goes down when we increase the parameter, we need to adjust it up. If it goes up, we go the other way.
But how much should we adjust it?
We scale that rate of change. That's the learning rate.
The learning rate? Why is that important?
Well, a big adjustment could overshoot the minimum, like trying to catch a falling ball with a giant net.
So, slow and steady wins the race?
Usually, yes. The rate of change of the loss could vary significantly nearby.
So, we're trying to minimize the loss in some way. How does this relate to the whole deep learning picture?
This is a fundamental step. We apply it repeatedly to parameters like weight and bias for different layers, tuning them to find the ideal values for the model.
So, the learning rate, that's like the speed control?
Precisely. It controls how aggressively we change the parameter values.
What if the learning rate is too small?
Then the process takes extremely long.
And too large?
We might overshoot the minimum, or even bounce around a lot. We'd never settle down.
So, the learning rate is crucial?
Absolutely. Crucial for efficient and effective optimization.
Right. How do you actually compute this rate of change in practice, using all the different parameters?
That calculation, called gradient descent, forms the basis of many algorithms.
Okay, so what happens next? How do we keep making these adjustments to find the best solution? So, Samuel, we're talking about calculating the rate of change of a loss function. You mentioned analytical methods are better than repeated evaluations. Why?
Yeah, repeated evaluations, they just don't scale well. Imagine a model with tons of parameters. You'd be checking the loss function around every single parameter, and it's incredibly inefficient. It's also hard to know how much to adjust, like how big a neighborhood to search around each parameter.
Right. So you're saying the size of the area around a parameter matters?
Totally. The loss function can change really fast, even if you just move a tiny bit. If you're not careful, your estimate of the best direction to go will be off.
So, what's the solution then?
The analytical approach finds the precise rate of change using derivatives. Think of it as zooming in to an infinitesimally small neighborhood around each parameter.
Derivatives? Can you elaborate?
We calculate the derivative of the loss function with respect to each parameter. This gives us the gradient. The gradient, it's like a vector pointing in the direction of the steepest descent of the loss function.
So you find the steepest downward slope, and that's the best direction to adjust your parameters?
Exactly. It's a powerful method for finding the optimal parameter values for your model.
How does this work with code? You mentioned a chain rule and stuff.
Yep, it's all about computing the derivative through different parts of the model. We take the derivative of the loss function with respect to a parameter by first finding the derivative of the loss with respect to the model's output. Then, we find the derivative of the model's output with respect to the parameter. These derivatives are multiplied together to give us the derivative of the loss with respect to the parameter.
So, It's all about linking different parts of the machine learning process?
Precisely. It connects the change in the loss with specific changes in the model's parameters. And we do it for every parameter to create that gradient vector. And in machine learning, we generally need to calculate this gradient for all the points in the dataset to get a good estimation. This is how we fine-tune a neural network's weights.
Interesting. And how do the functions in the code you mentioned work together to achieve this?
The code defines these steps. The loss function, like loss_fn, calculates how bad your model's predictions are. There are functions like loss_fn that compute the derivative of that function, which is very helpful to know how quickly the loss changes as you change the model's output. We have similar functions for the model and its derivative. Then, the gradient function grad_fn brings them together, multiplying the relevant derivatives and averaging them across all data points to produce the gradient vector for that step. These are fundamental building blocks of gradient descent and many more advanced methods used in deep learning today.
Okay, Samuel, so we've got this training loop. Can you walk us through what's happening?
Sure, Alfred. We're iterating to find the best parameters for our model. We start with some initial guesses, and then we adjust them repeatedly.
So like trial and error?
Exactly. We use a method called gradient descent to figure out the best adjustments. The training loop makes these adjustments.
And this epic thing? What's that all about?
An epoch is one full pass through all our training data. We update our model's parameters each time we process a sample.
So, the code we saw, it's basically doing this iterative process?
Precisely. We're running this loop for many epochs, optimizing our parameters step by step.
The learning rate, this learning_rate, is super important?
Absolutely. It determines the size of the adjustments to our parameters. A smaller learning rate means smaller adjustments in each step.
And what happens if the learning rate is too big?
It can lead to overshooting the optimal values. Your parameters will bounce around wildly. We saw that in the example. The losses blew up to infinity. The updates were just too aggressive.
So, we need to make sure to adjust the learning rate appropriately.
Exactly. It's often a crucial tuning parameter. If your learning rate is too small, it might take forever to converge to a solution. If it's too big, well, things can get unstable and even explode.
So we saw an example of making it smaller. Why is it a common tuning parameter?
It's because the gradient itself, the direction of the adjustment, might change a lot during training. A learning rate that works well at the start might be too big later on. You need something that adapts.
Interesting. So, the gradient's important. What does it actually represent?
The gradient represents the direction of steepest ascent for your loss function. In this process, you want to move in the opposite direction, the descent, to minimize the loss.
So, a bigger gradient leads to bigger changes in parameters?
Yeah, and if your learning rate is big enough, a large gradient can result in updates that are too drastic. That's what we tried to illustrate by reducing the learning rate. It helps avoid that.
Okay, Samuel, so you're saying we normalize the inputs?
Yeah, Alfred. We saw huge differences in the gradients for weights and biases. Learning rates that were good for one parameter could be way too big or too small for the other.
Right, that sounds like a stability problem. So, how did normalization help?
Exactly. We made sure the input ranges were more similar, around -1 to 1. This helps keep the gradients in a comparable scale.
And how did you do that?
We just scaled the input. It's a pretty simple multiplication. In this case, we multiplied the input t_u by 0.1.
So, you're saying that makes a big difference?
Absolutely. This rescaling keeps our gradients in a similar range, making it much easier to find good learning rates for the whole network. Otherwise, one parameter could update way too quickly while the others barely change.
Ah, I see. It's like having a single learning rate that works for everything now.
That's the idea. A single learning rate that works across all of our parameters.
Makes sense. So, was there anything else discussed in this normalization?
Well, we saw our loss decrease as expected in the example. It doesn't hit 0 exactly. Real-world data is rarely perfect.
So, even though this problem is small enough, why is normalization still important?
Normalization is crucial for complex models. Imagine hundreds or thousands of weights and biases. It's much harder to find stable learning rates without normalization. It significantly improves model convergence in complex situations. The normalization may seem unnecessary in this simple example, but it would be a game changer in large, sophisticated problems.
You're saying there are situations where it's absolutely needed.
Absolutely, Alfred. Normalization is a very helpful tool.
And what happens if we run for a lot more epochs?
We'll see the changes in the parameters getting smaller and smaller. We're essentially getting closer to a stable solution in terms of parameter values.
Okay, Samuel, we're visualizing data now. This plotting step, crucial, right?
Absolutely. Always visualize data first. It's like getting a feel for the story your data's trying to tell.
So, this code, it's plotting a model's predictions against the actual data points?
Yeah, it's comparing the line that the model draws to see how well it fits the dots, the actual data points. You can see if the model's predictions are scattered around the actual values or if they're clustered tightly.
And what's this asterisk perm stuff?
That's a Python trick. Imagine you have a bunch of model settings, and you want to pass them all at once. Asterisk params lets you unpack those settings into separate inputs, like individual arguments, rather than a single list. Makes the code cleaner.
Makes sense. So, the model's line looks good here, but the actual data points seem a bit erratic?
Exactly. The scatter of the data points tells you something. Maybe your thermometer or measurement device is unreliable, or maybe the temperature readings fluctuate significantly.
Interesting. Could this plot help identify issues with the data itself?
Absolutely. This visualization helps you see the patterns in the data and where potential errors might be, such as outliers or nonlinear relationships. A scattered plot might hint at noisy measurements, potentially affecting the model's accuracy. You can start thinking about filtering and cleaning up the dataset for training.
So, a crucial lesson here is that visualization isn't just for pretty pictures, it's for finding problems?
Exactly. It helps to uncover if there are issues in the input data or if the model needs adjustments. It's a great way to gain insights into the data's characteristics before we dive into more complex calculations or models. Without plotting, we're flying blind, so to speak.
Great points. So, the plot acts like a reality check?
Exactly. It's a sanity check on the data and model. It ensures that we're not drawing conclusions from faulty data. And it's not just for deep learning, of course, right? It's vital in any data analysis or modeling endeavor.
So, the line is linear, but the circles aren't, and that's the takeaway?
Exactly. Plotting allows you to see these discrepancies. We can then investigate why the data is so erratic and how that might influence our modeling. You can also identify outliers and anomalies in your dataset.
So, Samuel, you were saying that backpropagation is this smooth process?
Yeah, pretty much. If the functions are differentiable, we can find the gradient.
But what if the model is huge? Millions of parameters? Doesn't that get complicated?
Absolutely, it can be tricky. But that's where the beauty of AutoGrad comes in. It handles all the derivative calculations for you, automatically.
So, it's like magic?
Well, not quite magic, but pretty cool. The system works out the derivative expressions, instead of us having to write them out. It can handle extremely complex models.
So, we don't have to calculate the derivative expression by hand for each parameter, which could take forever.
Exactly. It's a huge time saver.
But what about the computational cost? Does finding the derivatives still take a lot of time?
It does involve some computations, sure, but you're right. It's one sweep through the entire model to compute the gradients of the loss function. It's quite efficient overall.
It sounds a little tricky to set up. Any pitfalls to watch out for?
Yeah, well, if the functions aren't differentiable, then we run into trouble. We need to find places where that's the case and make sure we handle them well, or the gradient won't be accurate.
What kinds of functions typically aren't differentiable?
Certain things like step functions, they have discontinuities and aren't differentiable everywhere. A good software framework will usually help catch those errors, but it's still a thing to keep in mind.
So, the key is this automatic calculation of the derivatives, and it's not completely effortless, but it dramatically speeds things up?
Exactly. It's a crucial part of how modern deep learning models are trained. It simplifies the process enormously, even for very complex models.
So, It's a crucial step in training a neural network. Then,
Absolutely. It's at the heart of backpropagation, allowing us to adjust parameters for optimal model performance.
okay, Samuel, so we're talking about automatic gradients now. How does this autograd work in PyTorch?
Yeah, it's pretty cool. Imagine your model as a series of calculations. PyTorch keeps track of these calculations, like a family tree.
So, like a lineage of operations?
Exactly. Every tensor remembers its origin, and PyTorch can trace all the way back to the initial parameters.
And that's how it finds the derivatives?
Exactly. When you compute the loss, PyTorch creates a graph of these operations, a kind of computation map.
This graph is essential. How is the backward pass done?
It's like following the reverse path in the graph. PyTorch starts from the loss and works backward, calculating the gradients of the loss with respect to each parameter.
So, it's just like a chain rule in calculus?
Basically, PyTorch automates the whole chain rule process. No manual derivations needed. That's the big win.
Interesting. And you were saying something about accumulating gradients? So, if I run it again, the gradient values keep adding up, right?
That's correct. You've got to zero out the gradients before each iteration to get accurate gradients in each training step.
So, resetting the gradients is vital?
Absolutely. Otherwise, your gradient values build up incorrectly, making your model learn very, very slowly or incorrectly.
Why not have the backward function reset automatically?
It's about flexibility. In complex models, you might want more control over when to reset. Zeroing them explicitly gives you more control.
Okay, I see. So, this requires underscore grad equals true is key. Can you elaborate on that?
Yes, it tells PyTorch to track all the tensors that depend on it. So all the results from calculations on that tensor are also tracked.
That makes sense. How does this with torch.no_grad thing work?
It essentially tells PyTorch to ignore that part of the computation graph when calculating gradients, so updates to parameters happen without impacting gradient tracking.
So, what does it mean to update parameters in place?
It means we're changing the original parameter tensor directly. Avoids unnecessary copying.
That's crucial for efficiency. Why is it beneficial in this specific context of autograd?
We don't need the new unupdated value of params in the backward pass. So, modifying params directly is fine here.
So, Samuel, we've talked about gradient descent. Now, you're saying there are other optimizers? Like, what's the deal with these optimizers a la carte?
Yeah, gradient descent is basic, but imagine training a complex model. It can be slow, even with adjustments. Optimizers offer different strategies to speed up convergence.
Speed up? How? Give me some examples.
Well, think of different ways to navigate a mountain. Gradient descent is like taking the steepest path down. Other optimizers, like Atom, are like taking more sophisticated routes, maybe zigzagging or using shortcuts, to reach the bottom faster.
So, how does PyTorch help us? Isn't it like choosing a different kind of mountain climbing gear?
Exactly. PyTorch gives us these different optimizers, like Atom, RMSprop, and more. They're already built in. We just tell PyTorch which one we want to use.
And how do we use them? Concrete examples?
We pass the parameters of our model to the optimizer. It keeps track of them. After we calculate the loss, the optimizer's step method adjusts those parameters based on its specific algorithm. Very handy.
So, there's a zero_grad. Step 2? Why?
Crucially important. If we don't zero the gradients, they accumulate. Imagine adding up debts. If you don't reset, your total debt keeps getting larger. The gradients need to be cleared between steps.
Got it. This zero_grad and step. Are they always needed in this order?
Generally, yes, they're typically in that order, though the exact placement in a loop is often less critical. Just always before backward. They're like the steps for calculating how much to change each parameter value.
What about different learning rates?
Different optimizers handle learning rates in different ways. SGD, a plain gradient descent optimizer, requires a learning rate as input. Atom, for example, often adjusts the learning rate adaptively during training, which can be very useful for complex models.
So, what if I use Atom instead of SGD?
you'll likely get different results. Atom is often more efficient, particularly with complex models where SGD might struggle. But it really depends on the model and the data. You might even get better results with SGD in certain cases. It's an exploration process.
So, the process is essentially this. Define the model, loss function, parameters, optimizer, training loop. Calculate loss, update gradients, update parameters, repeat. Is this correct?
Precisely. This streamlined approach makes training deep learning models manageable. It's not just about the optimizer. Choosing the right model and data is key too.
So, Samuel, you mentioned overfitting. Can you paint a picture of what that looks like in real-world terms? Like with a thermometer?
Sure, Alfred. Imagine you've got this thermometer that measures temperature, but it's a little wonky. It uses a really complicated formula. It fits the data points you give it perfectly, but only those specific points.
So, it's like memorizing the answers instead of learning the underlying principle?
Exactly. It's trying too hard to hit those specific data points, and it ends up making a really weird function to connect them. This curve might be super accurate for the data you fed it, but completely wrong if you give it new temperature readings.
Makes sense. And how do we avoid that?
We use a validation set. We set aside some data that the model hasn't seen during training. This validation set acts as a reality check.
So, we train the model, then test it on something it hasn't seen before?
Exactly. We look at how well the model does on both the training data and the validation data. If the model does great on the training data, but terrible on the validation data, we know we're overfitting.
Gotcha. And what's the deal with model complexity? Simpler is better?
Well, it's a balancing act. A really simple model might not fit the training data well. A complex model might overfit. It's important to find a sweet spot.
So, we start with a complicated model and make it simpler?
Yep. We make it more complicated until the training loss goes down. Then, we scale it back until the validation loss starts rising. That's where the optimal complexity lies.
Interesting. And how does the code, split the data?
The code shuffles the data. It randomly reorders the data points. Then it splits that shuffled data into two sets, training and validation. A crucial part is that it uses a portion of the data for validation, and the rest for training.
And is there a general rule for determining how much data to put aside for validation?
No hard and fast rule. 20% is a common starting point, but it depends. Sometimes more is needed, depending on the size of your dataset.
Thanks, Samuel. That really helps. So, if my validation loss is consistently higher than my training loss, what does that tell me?
It tells you you're probably overfitting. The model is doing well on the data it's seen, but isn't generalizing well to new data.
How about if the loss for both doesn't decrease at all? What does that suggest?
That your model isn't learning anything. Either the model isn't complex enough, or the data doesn't have the information needed to make accurate predictions. Or, there are other factors. Need to look at the loss curves more closely.
So, Samuel, you're saying AutoGrad isn't confused by evaluating the model on both training and validation sets?
Exactly. Each evaluation creates a separate computation graph.
Okay, but how does that work? Imagine I'm building a model to predict housing prices. I train it on lots of data for houses in the city and then evaluate it with houses outside the city.
Right. The training data's graph only influences training. Validation's graph is separate, so it won't mess up training.
So, if I call backward on the training loss, it just looks at that particular graph?
That's right. It calculates the derivatives only related to the training data and the training loss.
Ah! So, a huge computational advantage.
Potentially, yes. But we have to be careful. We aren't finished yet.
Why not? What am I missing?
We're building these graphs for the validation set, right? Why bother? Building the AutoGrad graph does take some time and resources. Why not just use the model as a function?
You mean without tracking the computation?
Exactly.
So, how do I do that practically?
Using torch.no_grad. It's a block where anything inside is calculated normally, but no gradient calculations are performed.
So, it's like a temporary switch for AutoGrad?
Precisely. Great for validation. It can save us resources, especially on large models.
So, when are you likely to see a benefit from using torch.no_grad?
When you have huge models with millions of parameters, and validation steps are frequent, you'll notice a savings then.
So, is this why we see the assert val_loss.requires_grad equals false line in the code?
Yes, that's precisely why. It's a check to ensure that we've correctly switched off autograd for the validation portion. It's best practice to confirm.
What are some common mistakes people make concerning this?
Sometimes, people forget to use torch.no_grad. That leads to unnecessary gradient calculations during validation and increased memory usage.
Good point. Is there anything else we should be careful about with this?
The requires_grad attribute being false in the no_grad context doesn't always guarantee no gradients. It's smart to use detach, as well if absolutely needed.
You mean for extra certainty?
Exactly. Detach is a simple function that creates a new tensor, disconnected from the computation graph, ensuring no gradients are tracked.
Very helpful, Samuel. This torch.no_grad context is an important optimization. So, we've explored basic model optimization. Now, you're saying neural networks are the main course?
Exactly. Simple models are great for understanding the mechanics, but neural networks are much more powerful.
Why are they so powerful? What makes them different?
Neural networks have many layers, like a complex feedback system. They can learn very intricate patterns and relationships in data.
So, we're still talking about learning from data?
Absolutely. They learn from examples, just like before, but their architecture lets them handle more complex scenarios.
Like what kinds of complex scenarios?
Image recognition, natural language processing, even predicting stock prices.
The torch.nn module. Is that a library for neural networks?
Yeah, it's a crucial Python library within PyTorch. It provides the tools to create and train different kinds of neural network architectures.
So, why use PyTorch for this thermometer problem if it doesn't strictly need it?
It's about learning how to build neural networks. This simplified problem lets us get familiar with tools and understand their use. You see, it teaches principles that apply to more complicated applications.
But a linear equation could solve that thermometer problem, right?
Right. But neural networks teach us a more general approach, allowing for solutions on more complicated datasets. You gain that versatility and adaptability.
That makes sense. So, we'll use neural networks for the same kind of data analysis, but now it's more sophisticated.
Exactly. It's like learning to drive a car versus learning to build a rocket. Simple models are great for the road, but the rocket requires specific tech. This approach allows us to build those rockets, or at least develop the necessary skills.
So, what's the next step then? We're finally going to work with neural networks?
Yes. In the next chapter, we'll dive into neural networks, using this problem to exemplify how they're used and how they are trained.